So our topic for today is Chapter 3, Modeling. We're going to, we actually did a little bit of this in like 2.4 or something like that, or 1.4, where they had you just set up some differential equations, but back then we didn't know how to solve for them yet. So this time we can handle the first order differential equations, some, definitely not all. But we can handle some differential equations and be able to solve for them and apply them to problems. And so let's do some of that. And like I said, I think I'm just interested in just doing a bunch of problems and see how they would work out. So in your textbook, there's a whole growth decay problem stuff, but I think that problem is pretty much figured out back when we were doing pre-calculus. So, and the setting up the differential equation is not that big of a deal. So I'm going to jump to Newton's law of cooling as our first example. Uh-oh, let's try that again. Newton's law of cooling talks about how the rate of change of temperature, how the temperature changes, and then with respect to a specific environment. And the first Newton's law of cooling depends on the exterior body temperature. Maybe this isn't the one I wanted to do. All right, let's see if we can work it out. So if you put a roast in the oven, and the oven's set at 200 or 350 degrees, and then your roast is whatever room temperature is, or maybe even colder because it just came out of the freezer or fridge. When you put that into the oven, then you can the temperature of the roast will start going up, right? It will go up to whatever the temperature of the oven is, but it's not going to go beyond that. You know what I mean? If you have the oven at 350 degrees, then your roast will never reach 400 degrees. Unless it's a magic roast. But we don't have that. So Newton's law of cooling says that the way the temperature increases to whatever the environment's temperature is it's called a logistic equation. It has some exponential properties. But it also has an asymptote. So like the population of the Earth can usually be modeled with an exponential function. But you know, exponential function just goes up to infinity, right? But the Earth is can't hold an infinite number of people. So eventually the population for the Earth has to level off somehow. And so there's a leveling process and there's a maximum amount. All right, here's a slightly modified version of the logistic problem. A rate in which the body cools also depends on its exposure to a surface area that it's touching, and S is a constant. Then the modification of the original logistic equation is basically the original equation that they're talking about is essentially the same thing without the S. And then we have a constant K. If it's cooling, then your K is negative. If it's heating up, like putting something into the oven, then your K is positive. And then Tm is a constant temperature. So that's like the room temperature or the temperature in the oven or whatever. Suppose 2 cups, A and B, are filled with coffee at the same time. Initially, the temperature of the coffee is 150 degrees. The exposed surface area of the coffee cup in B is twice the surface area of the coffee cup in A. After 30 minutes, the temperature of the coffee cup in A is 100, and then they ask if Tm, that's the external temperature, the temperature of the environment, so that's essentially room temperature. What is the temperature of the coffee cup B after 30 minutes? So they want you to do a comparison here. All right, let's try to do this problem, and let's take a look at this problem from coffee cup A's point of view. And then we'll approach it the same way to take a look at it from the B's point of view. Coffee cup B is twice as surface area. Wait. Coffee cup B is twice the surface area. The temperature is twice of that of coffee cup A. So when we get to the B analysis, we'll just, instead of multiplying it by S, we'll just call it 2S and see what happens. All right, so the process is going to be, so our independent variable is little t, and our dependent variable is capital T, and everything else that's around here is constant. All right, so dt is equal to KST minus Tm. So at this point, the only thing we really know is Tm. What's Tm? That's the room temperature at 70 degrees. We also have this information that the coffee, before it was poured into the cup, or the instant that it was poured into the cup, the temperature of the coffee when this whole thing started is 150 degrees. So we can call that our IC, our initial condition. So we have an IVP, an initial value problem. All right, this looks easy or hard. What do we do here? How do we solve for this? It's a separable differential equation. So I'm going to leave the Ks with a little t, and then the capital T I'll group together. D capital T, T minus 70 is equal to Ks. Those are constants, dt. And then we'll integrate both sides. So ln of t minus 70 is equal to kst plus another constant. So that constant is, or we'll use the initial condition to solve for that constant. Okay. Now, I think I mentioned earlier a while ago that you can solve for the constant at any point, but I think in this case it might be good to work through this and solve for t, and then eventually solve for the constant, because these logistic equations, the first few differential equations, they look nice when you solve for it all the way, because how we play with the constants, they kind of merge over. So let's take the exponential, the e of both sides. So t minus 70 is equal to e to the kst plus c, and so that's e to the c, which we can take out as a constant. So this c became e to the c, and that e to the c just became another constant that we'll call capital A. That's usually turns out your initial condition, usually. So if we solve for t, we get the function by itself explicitly, a e to the kst plus 70. So we're interested in solving for a. We also, s is a constant. They didn't tell us what s is. And maybe the cup was like, 65 degrees or something like that for one cup, and then the other cup is twice as twice as hot. But we'll leave S alone for now. But the A is an unknown constant. That's your constant of integration that we got. And the K is also an unknown constant. And then we have this other information about 30 minutes later. We'll use that to solve for K. But I think the easy solve is to use your initial condition to solve for A. So when t is equal to 0, when little t is equal to 0, capital T is equal to 150 degrees. And so we'll use that information. A e to this whole power becomes 0 plus 70. So e to the 0 power is 1, and A is equal to what? 80. And so our A is equal to 80. So our function here, t of little t, turns out to be 80 e to the kst plus 70. Okay? So we'll box that, but we still need to find out what k is equal to. So we'll use that information where 30 minutes later, and we'll take the time 30 as our time in minutes, t as a time in minutes. So when t is equal to 30, the big T is equal to 100 degrees. So we'll use that information to solve for k, and that will give us 100 is equal to 80 e to the ks times 30 plus 70. So we'll bring the 70 over. You get 30, and then 3/8 is equal to e to the 30 ks. And then we'll continue to solve for k. Take the ln of both sides. Ln of 3/8 it should be a negative number, right? Is equal to 30s times k divided by 30s, and you're going to get 1 over s. This is an s. 1 over s ln of 3/8 divided by 80. That's what your k is equal to. So when you put that back in, you have a new and improved function. I don't know. 30. So our new and improved function is 80 e to, we just found k, and the s's will cancel. And so whatever this is, did you guys figure this out yet? I heard a little bit of calculator noise. If not, I'll just write it all out. I don't want to. 0.1326. 0326? Can we get a confirmation? We got it? All right, we'll go with that. The s's go away, so this is your nice function. What? Oh, for cup B. Yeah, so you just put it to where? Well, you would put it up here. So this is our K. And what we're going to do is, we're essentially going to multiply something by 2. So this is for cup A. We should call this TA. T sub A. Now, if we go through the same process for cup B, for cup B, what we'll have is essentially the same thing that we have for cup A, with the same K, right? So your T sub B sub T is equal to 80 e to the whatever K was, I'll put K in there, times, now instead of S it's twice as hot, right? This is your S, so it'll be 2S times T plus 70. And it turned out that this is 2S, right, not 25? So it turns out that K was equal to 1 over S times, this is an S, times negative 0.326. So the S's would cancel again, and then so you just basically double the exponent power, and then that's going to be your result. So, and let's see if this actually does make sense, right? It should be about, it should be a little bit hotter than 100. Let's think about this. You got the coffee cup itself. Coffee cup B is twice as warm as coffee cup A. What? Oh, twice the surface, twice as big. Oh, they're talking about surface area. So it's twice as big as a coffee cup A. So should we expect this to be cooler or warmer? All right, so let's see what happens. So it should be less than 100 degrees, right? So let's take your calculators out again. We want to TB at 30 degrees or 30 minutes is negative 0.0652 times 30, and take that as a power of E, multiplied by 80, and then throw in a 70. What do we get? 81.2 degrees. Okay, so that looks good. It's kind of like what we anticipated. It's a little cooler. Okay. So really the only differential equation we're doing here is this step when we have the initial value problem, we separate it, we integrate, and then we get a solution. After that, it's just algebra. All right, any questions? Yeah.
I didn't understand the part where you say A, the letter A times B to the power of A S T, that will be plus C in that.
This one?
Yeah.
This one is,
And also C, right, the power.
yeah, so e to the c. When you use the exponents, it's like e to the kst times e to the c. And so since you're multiplying e to the c, it's just another constant. So I decided to call that something else instead of e to the c. And that's a common thing that you'll see that a lot in things that deal with differential equations. Anything else? All right, let's do another problem. So you had a mixture problem in your homework, but I took it out. Figured I want to trim it down a little bit, but I decided to keep the series circuits problems in your homework. So let's talk a little bit about that. I have to say I don't know much about circuits, but if it's put in the context of differential equations, then we can just talk about it in the context of differential equations. So I think the drawing that they had an electrical circuit that looks like this. E is the voltage that you have going around the circuit, and then this particular one goes through what? Inductor. So this is an inductor. And it's usually denoted by L. And then it goes around. And then it's probably and then you have a resistor, and that's usually denoted by R. So what you're measuring here is a current that goes around this circuit. So the current is a function of time. A lot of times it could be seen as something that's constant, because we'll see what happens when we solve for this. But the current is a function of time, and that's you get a differential equation out of that. So it turns out that the voltage that's put out is equal to the inductor times the rate of change of the current plus the resistor times the current. Okay, then the second picture over here, maybe I should take this picture out for now. The voltage drop, the capacitor. Let's work on that later on. Can I just cover that? I wonder. It's weird. All right. I just make it white, I guess, huh? With no outline. Outline's fine. All right. So let's do an example of this. And I think the problem I was looking at earlier that I accidentally didn't save was a problem that's very similar to your homework. Where is it? So an LR circuit, let's take a look at this one. So this is a little tricky because we have a piecewise function, and so if we just deal with it in those pieces, then that would be, I think it should all work out, which probably means we have to do a couple of differential equations for this. But I think these differential equations are fairly simple. So here is your voltage. The electromotive force is applied to the LR circuit with an inductance of 20 henries. So the inductor L takes in that value, and a resistance of 2 ohms. And I think for these problems, you know, some of these are these are the units that they use. And they want you to find the current if the current at 0 is equal to 0. So this is our differential equation. We'll start off with that differential equation. And we have L, so let's put the values for L. Let's write it down. So L is equal to 20 henries. The resistance is 2 ohms. And we're looking for I. And so the voltage, so imagine that they're providing voltage from the time 0 to 20 seconds. And then after that, they cut off the voltage. So now the voltage is 0. So they want you to figure out what happens. So our differential equation will come in 2 parts. The first part is when t is between 0 and 20, your differential equation would be L times di dt, and L is equal to 20. So I'm just going to put those values in. R times I is equal to 120 volts for that first part. All right, so let's go ahead and try to solve for this differential equation. It looks like, what does it look like to you? Yeah, so it looks like a first order linear differential equation, right? So let's practice our first order linear differential equation techniques. I think a lot of us need practice on that. Yeah, after I graded the quiz, I thought, well, that's too bad. All right. So the first thing we want to do is we want to wipe out the outer function. So the nice thing is that these are all constants, so we don't have to deal too much with weird functions. So this becomes a 1/10 maybe, 1/10 I, and this becomes a 6 or 66. So this is our P function, and so if we think about our integrating factor, mu of x, this is equal to e to the integral of 1/10 dt. So that's just e to the 1/10 t, right? So that's your integrating factor. So imagine your integrating factor, multiplying it through. I don't want to do this, but given the quiz, I think I have to. We're going to take this and multiply it through. So this is e to the 1/10 t di dt plus 1/10 e to the 1/10 t times I is equal to 6 times e to the 1/10 t. So what I did there is I multiplied everything by the integrating factor, and what you have to realize is that the left-hand side is actually a product rule where you had taken the derivative of two things. And the two things that you took the derivative of looks like it's e to the 1/10 t times, and then the other thing that you took the derivative of is I. And so if you want, you should take the derivative of this product to make sure that you got the thing up on top. Okay? So it's always going to work out like this because that integrating factor is that special integrating factor where you produce a product rule out of it. And so at this point, what you want to do is you want to integrate both sides to solve for I. That's your main goal, right? To solve for that function. So integrating a derivative is going to give you the original function, which is a product of two things. And integrating this would just give you whatever this is, 60, right? And here's where you have that constant. So don't forget the u substitution on this right-hand side integral. And after you do that, you are essentially solving for I of t. And so you divide this out. Now, this has two terms. Don't forget the plus c. That was a few people's mistakes, is that when they divide this out, they left the plus c outside. But the plus c will take in this thing when you divide it out. So when you divide the first, you can divide term by term. This will just cancel the e to the 1/10 t. And then the second term will give you that c divided by e to the 1/10 t. Or you can think about it as multiplying by 1/10 t. So what do? We initial condition it. We put 0 in for t and set it equal to 0 because that's the initial condition. So when you put 0 in for t, you're going to get 60 plus c times e to the 0 power, which is 1. And I would also equal to 0. So c is equal to negative 60. And that's your function. I of t is equal to 60 minus 60 e to the 1/10 t. Suppose you can factor out a 60 and write 60 just one time, but this will work for us. Okay? All right, so that's the first part. Now, this is a piecewise function, and we've only dealt with this from 0 to 120. So after 2 minutes, what's going to happen? They turn off the voltage. So what's going to happen to the current then? So when t is bigger than 120, we have a new differential equation that looks awfully similar, except that the e function is 0. Right? So this also looks like a first order linear. Oh, I thought it was 120. Yep, sorry. So 20 seconds. All right, so in 20 seconds, what's going to happen? Well, we'll have this as our differential equation. And now, looking at the differential equation, this looks an awful lot like a first order linear differential equation, right? So do we want the same approach? It's separable. Actually, the first one was separable too. Nobody caught that one. Okay. We got to practice. Decided to practice because the quiz really sucked. And so now that you've seen the first order integrating factor again, I hope this will work out a little bit better for you. All right, so it is a separable differential equation, so let's separate it. We want to still divide by 20, but move the I to the other side. So di dt is equal to negative I, and the the coefficient is 1/10 again. And to separate it, I'll keep the constant 1/10 on the right side, so di over I is equal to negative 1/10 dt. And here's our separable dE that we integrate. And we get ln of I on one side is equal to negative 1/10 t plus c. Should we even do this? Yeah, we're doing it already. So the function that we're looking at is e to the negative 1/10 t plus c, or times e to the c, or times a. So we'll look at it from that point of view. Now, there's a couple of tricks to this. I probably should have addressed this earlier, but this is for t bigger than 20. So what we could do, or we could have done, is done an offset so that we are looking at this at 0, or we can try to pick it up from here when t is equal to 20. But we had an initial condition for the first one. Our initial condition was I of 0 is equal to 0, but here we don't have t is equal to 0. We have t starts off at 20. So we can pretend that it starts off at 0 and then do an offset, but we still need to know what the y value is. So how are we going to approach this? How are we going to find our, quote, initial conditions here? So in other words, I really should start at t is equal to 20. So let's start at t is equal to 20. But for us to figure out your IVP, let me write this a little bit neater. We need to know where to start. How do we know where to start? Anybody? Yeah?
Is this where the other equation ends?
This is where the other equation ends. This is our other equation, right? And our first equation over here goes from 0 and stops at 20. And right there, something else is going to happen. So, assuming this is continuous, which it probably is, we can just figure out where this thing ends, and that's the new starting point for that new function. Does that make sense? Which means we need to borrow from this information. We need to figure out what I of 20 is from this function. So we need to put 20 in there and figure out what this is equal to. So anybody with their calculators, quick on their calculators? Do you want me to take out my own calculator? If I do everything myself, then it's like watching a video. Maybe I should just record myself. Wait, I am recording myself. What is it? Say it again. 51.88. Can we get a confirmation? Thumbs up. All right, we're good. 51.88. So we'll use that as our initial condition when t is equal to 20. So that's how we're going to solve for a. So 51.88 is equal to a e to the negative 1/10 times t. In this case, we're starting off at 20. So a is equal to, it looks like it's going to be the ln of 51.88 divided by, oh, that'll probably be times. Yeah, e is a constant. Oh yeah, we don't need the ln. Oh, thanks. Sorry. Oops. Got carried away with my ln's and exponential functions. Yeah, you don't need an ln here because a is a constant that's sitting outside. That's what you're solving for. So 51.88 divided by that thing, which I think is e to the negative 2, right? Yeah. All right, what do we get? Anything? What is it? 383.84. 0.34? 383.34. All right. So that looks like our constant. And so to wrap this up in a nice package, our final answer should look like a piecewise function. So I of t is equal to, it's going to be, I'm going to take a 60 out and just say 1 minus e to the negative 1/10 t, so long as t is between 0 and 20. And when it's bigger than that, it's this constant, 383.34 times e to the negative 1/10 t. Yeah. Uh-huh. Yeah, so I kind of, sorry I didn't explicitly do that. I put that back into here, and then the rest of that is e to the, so is this okay? All right. All right, I'd be interested to see how this thing would look like in a graph, and so let me pull out a quick graph. Oh yeah, that's 20. Don't you see that too there? All right. Okay, so let's see how this thing is going to look like. I could do piecewise functions here. Let's say 60 times 1 minus e raised to the 1/10, so the negative 0.1 times x, and I want this from 0 to 20, and then after that I want 383.34 times e raised to the negative 0.1 x, and this one I only want to see this from 20. There's 0 again. 20. Let's see the graph. That's where it starts off. Can't really see it until we zoom out. Nice. So looks like the current is flowing really nicely, and then you turn the power off, take out the voltage, and then the current goes back down. All right, let's take a quick picture and move on. Any questions? Oops. All right, so this is one type of circuit. The other type of circuit is, what is it called? This is an RC circuit, they call it. So let's take a look at one of these problems. voltage drop across a capacitor with capacitance given by Q over C, where Q is a charge on the capacitor. And there's another relationship between the current and the charge. It turns out that the derivative of the charge is equal to the current, and so there's a relationship between Q and the I, the previous equation that we had. But essentially, you come up with a differential equation. The drawing for this, I think, looks like we have the voltage here and going through a resistor. And I think the way you draw the capacitor is a break in the circuit. So the circuit has to jump through. So there's the resistance and the capacitor. Okay, let's see if we can try to do one of these problems. We need an RC circuit example, number 32. We got a 200 volt electromotive force applied to an RC series circuit, which the resistance is 1,000 ohms, and the capacitance is 5 times 10 to the negative 6 farad. Find the charge on the capacitor. Now they give us the current at 0, and they don't give us a charge, so we need to find out. You need to highlight this relationship between the current and the charge to help us find the charge. And then they want us to find the current and the charge at 0.005 seconds, and then see what happens as t approaches infinity. Okay. So we have the constants that we need, the R and the C, and then we have the E, the voltage is given to us also. That's 200 volts. So let's see what happens. So R is equal to 100. Thousand, and then the C is 5 times 10 to the negative 6th. So let's see if we can work this out. We have 1,000 dq dt plus 1 over 5 times 10 to the negative 6th times q is equal to constant 200. Okay, same business. We can think about this as a first order linear differential equation, or we can think about this as a separable differential equation. First thing I would like to do, either case, is to just divide out by that 1,000. Scientific notation here. Divide this out, we get 1 over 5 times 10 to the negative 3 or negative 9? Negative 9. Q is equal to, and now we have to divide this by 1,000. So that's 2/10, right? 1/5. All right. So should we do this as a linear differential equation? So if you're looking at this and you have a bunch of constants, or even if your p is constant, you know that your p, your integrating factor is going to be e to the integral of that constant, right? Which is essentially just multiplying by t. So why don't we approach it that way? And this time I'm going to skip a couple of steps and just go to the part where we're integrating already. because I know this will end up after doing the integrating factor. We know that this is going to be a product. So the product, yeah. Well, that's what I was asking. People said -9.
Well, you're dividing by 1,000. But it's not. In the first place, it's so small. You would have a negative because you have 1 over. Oh, the negative. That's the equation.
You guys working it out? What's 200? Is 200? Yeah, so you multiply by the reciprocal. We're talking about this number here, right?
Yeah.
It's 200? Okay. Really? So what you're saying is that I erase this and put 200. All right, I'll go with that. So this is our differential equation. So back to the integrating factor business. Your integrating factor will end up being e to the 200t, right? And then we know that this left-hand side, after you do the integrating factor, will be a product of the integrating factor times the unknown function. And then here you have 1/5 e to the 200t that you want to integrate. Okay? So I skipped a few steps, but the idea is to find the integrating factor, rewrite the left-hand side as a product rule, and then undo the derivative by taking the integral of both sides. So that's what happens. All right, so q of t is equal to, I'm going to bring this over to the other side already, e to the negative 200t, because I have to multiply by the reciprocal or divide by it. And then here, when I integrate this, I would get, what would I get here? What is it? $1,000? E to the 200t plus that constant. 1 over 1,000? Okay, so 1,000 plus the unknown constant e to the negative 200t. So this is our charge, it looks like. Now we want to solve for c with this initial condition, but the initial condition doesn't have a q in it. The initial condition has an I. What? Oh. All these constants. Is that cool? All right. Initial condition. So our initial condition issue is that our initial condition is given as an I, the current, but we want the charge. So what we need to do is figure out the relationship between the charge and the current. It turns out that the I is equal to the derivative of Q. So if we take this Q function and take the derivative of that, we're going to get I, and maybe we can solve for C that way. So I is equal to dq dt, which is equal to the derivative of this thing. Now the 1 over 1,000 is a constant, so that's going to go away. I will have C times E to the, well, I have negative 200 or something, right? Negative 200 C times E to the negative 200t. Is that right? So that's I, and if I put 0 in for I should get 0.4. So 0.4 is equal to negative 200c. E to the 0 is just 1. So my C is equal to, yeah, whatever that is. Negative 0.002. Okay? So that's the constant, C, different from the capacitance, C. So my Q of T is equal to 1 over 1,000 minus 0.002 e to the negative 200t. And my charge, or my current, sorry, is equal to that same constant times 200, which is 0.4, right? It's 200 times that constant that we got. Is it 0.4? So negative, negative cancels. It looks like a 0.1. Something wrong? That's right? It should be right. E to the negative 200t. All right, so these are my two functions. If they want to figure out what the current and the charge are from when t is equal to 0.005, then just put 0.005 in for t and get the value. More interested in what happens, determine the charge as t goes off to infinity. What happens as t goes off to infinity? So as t goes off to infinity, this thing, e to the negative 200t goes to 0, right? And so that's going to wipe off whatever constant we had found, and so it just becomes that constant. What's this thing called? Transient term. Right? So when you take the limit as something goes off to infinity and that thing disappears, that term disappears, that's a transient term. All right. I didn't quite answer the 0.005, but you guys can plug that in and figure it out. Question? That was given here. Okay, we good? All right. There was one problem I wanted to do from the next section. I can't remember what it was. I think I was just going to do a problem from the homework. Oh, there's only 3 problems. Oh yeah, I was going to do the last one. Yeah. I don't know. All right, well, let's see. Probably not going to finish, but let's get started with this anyways. So the next section here is still modeling, the idea of modeling, but it's modeling, the first section was modeling first order linear differential equations. Here it's looking at nonlinear models. So let's take a look at this and see if this is nonlinear. All right, this says determine the differential equation for a velocity of a mass sinking in the water that imparts a resistance proportional to the square of the instantaneous velocity with a constant proportionality k. It also exerts an upward buoyant force whose magnitude is given by Archimedes' principle, which states that the upward buoyant force has a magnitude equal to the weight of the water displaced. What? Assume that the positive direction is downward, and V is the volume of the object, and P is the weight and density of the water due to gravity. All right, so this probably has something to do with mass times acceleration, Newton's second law. Let's start off with that. So the differential equation for velocity, mass sinking in water. For the velocity of a mass sinking in water that imparts a resistance proportional to the instantaneous velocity, to the square of the instantaneous velocity. So it's equal to proportional to the square of the instantaneous velocity and also exerts an upward buoyant force whose magnitude is given by Archimedes' principle, which states that the upward buoyant force has a magnitude equal to the weight of the water displaced. So the force has a magnitude that's equal to the weight of the water displaced. Plus W, rho V. So the volume and P or rho is the weight density. Okay. So it looks like we also have gravity involved in here. How's gravity play into this? The acceleration is dv dt, but the force is also equal to the mass times the gravity, right? So let's call it mg. And acceleration is dv dt. So it looks like we're getting closer to our differential equation that has the velocity function in it. Huh. Well, I think I have three things here. That doesn't look right.
I think it's F equals mg minus kv squared minus p big V.
So F equals mg minus kv squared minus rho v. That's the volume. And then that's different from little v. And then the force is equal to mass times acceleration. But I think we need the acceleration part. So the force equals to mass times acceleration, and the acceleration is your dv dt. And so if you write your dv dt equal to mg minus kv squared minus rho capital V for volume, then you have your differential equation. All right. So that's our differential equation, and we want to try to solve for that. How would you solve for this differential equation? What? You got to put it into a form. Let's see, what form? Well, we can take the m out, and let's scratch this out. Looks like it's not. dv dt is equal to, divide everything by m. We have just g minus k little v squared over m minus rho capital V over m. Let me highlight the variable. There's no t's in there. Oh, what's it called when you don't see the independent variable on the other side? It's an autonomous differential equation, which means, what can we do with this? It's a separable differential equation. All right. So why don't I just separate it? And it looks like maybe if I just rewrite it like this, g minus rho v over m minus k over m v squared is equal to dt, because it looks like I can't, because there are three different terms there, I can't separate those terms, so they come as one whole big package together as with a dv. And so these are just constants, so we should just be able to work with them as if they were constants. I think my suggestion here would be, if we knew those constants, there might be a chance of doing an integration by, if this somehow factors, we might be able to do a partial fraction. But if you usually have a squared, a v squared, or the variable squared in the denominator along with other terms, what possible technique might you be interested in using? Integrating technique. So this boils down to a Calc 2 problem, integral calculus problem, where you just have constants that are messing you up. But how would you deal with this? No, because I can only do partial fractions if I'm confident that this thing would factor. And at this point, I'm not sure because I don't know what these constants are. If they factored, boy, that would be great. Trig substitution. So I would go with the trig sub here by letting b equal to something with a sign, some coefficient with a sine theta, and then see what you can get. Or you can just put it into Wolfram alpha and see what it tells you, and then that's your answer. All right. So we seem to be out of time. I will try to have a review sheet online by maybe tomorrow. But if not, definitely it'll be up there by Tuesday so that we can do a little review. And then don't forget that you have a test here on Thursday, a week from today. Okay, and I'll give you pretty much a good outline of what's going to be on the test. Okay, see you guys.